Hey everyone, welcome back to another episode of A View from Earth, the science podcast where we interview local Colorado scientists about the work that they're doing and bring that to you. So I'll introduce myself real quick. My name is Colin Sinclair. I'm an undergrad at CU Boulder, and obviously I work at the Fisk Planetarium as a presenter when it's open, but right now when it's closed, I work as a co-host for this podcast alongside Tara Tomlinson. Hi, Tara.
Hi, Colin. My name is Tara. I am a planetary scientist and a CU alum. I'm also the outreach coordinator for Fisk and do some other Fisky things, but of course right now, this is my primary existence, is hosting this podcast.
We're also joined by John, our producer, John Schiller. Hi, John.
Hello, I'm John. I'm a graduate of the CU Astronomy Department, and I work at Fisk normally doing shows, running the planetarium, also producing and editing and doing all sorts of other stuff on some of the short films or documentaries that we make in-house at the planetarium.
Basically, people like John make it possible for the rest of us to do anything. So
shucks.
So today we're going to be talking with someone named Dr. Kelsi Singer, who is a geologist and geophysicist is that right, Tara? Is that the right? I guess I'm looking for the most general term for someone who studies craters is really what we're going to be talking about today. I don't know if there's any lines that exist that I don't know about it.
It's subtle, but yes.
Okay.
and you can study craters and either be a geologist or a geophysicist.
Interesting.
But a lot of us are kind of do both.
Okay, cool. Well, anyways, that's who we're talking with today. And we're going to be talking about craters. And so it's going to be a lot of fun. I had to warn both Tara and Dr. Singer that I am not a crater person because, Tara is, right? So we have two very established craterologists. Yep. And
those are words.
Yeah, it's fine. And then there's me, and I was just like, hey, I might ask you guys to slow down and say what you're talking about because I don't really know anything about this. But it was surprisingly easy to follow. I mean, I think that Kelsi did a really good job of making sure everything was understandable, Mm-hmm. I appreciated that. So that was nice.
Yeah, and cratering as a science has a lot of levels. On a sort of high level view, it is really easy to understand.
Sure.
You take one big thing and you throw it against another big thing and it makes a hole. The end.
Right.
And it gets more complicated from there down, but that's the basics. It's an accessible concept. I think a lot of people have experiences with throwing something and it making a dent. So it's a relatable science.
Yeah, absolutely. Well, I thought it was really funny. At some point in our interview, we started talking about simulating or replicating planetary scale impacts. And I just, in my head, I was like, imagine society at the point where we're advanced enough that we can say, hey, we want to see what actually happened, at the Chicxulub crater that may have, that probably led to the extinction of the dinosaurs. We want to see that for real. And then they have the power and the technology to do that. That would be crazy.
That would be really, really cool. Unfortunately, we can't do that yet because, we'll talk about a little later, these things are happening at huge speeds. Like at Europa, the average impact rate is about 26 kilometers a second. And we do not have things here on Earth that will go that fast.
Yep.
So, we rely on a lot of computer modeling, which is still really fun and really cool and makes very pretty pictures.
Oh, yeah.
But it's not quite as satisfying. I mean, that's just me. I want to throw things at other things and make them explode.
Yeah. Well, I think that's the ultimate culmination of your studies, right? Is to see it actually happen. Obviously, we can, plug in the laws of physics into our computers and write a simulation and watch what comes out, and that's really interesting. But watching it actually happen, I think, is you can't go further than that. That is the the ultimate way to see what's going to happen.
Yeah, that would be absolutely amazing. Right now, we do have I know recently, people that I personally know have been seeing fresh impacts on places like Mars and the Moon. So we can see like the Mars Reconnaissance Orbiter goes around Mars every couple of days, I think.
Right.
And so it'll pass over the same spot one day and there's not a crater, and then 2 days later there is a crater.
Right.
Or I even know a girl who looks for impact flashes on the Moon. So we can't see it's not high enough resolution that we can see a thing hit the surface, but we can see the flash that happens when this huge explosion basically goes off.
Yeah.
So she writes code to detect those, which is pretty neat. And then the ultimate goal is to then like send that to a spacecraft who can pass over that and go check it out like as soon as possible.
Right. Well, that reminds me of, we may have talked about this on the podcast, but it might have been with somebody else. I was talking about, there's like this Twitter network of like, if you send, I can't remember how it works, but if you send a certain, like the body of the tweet has some text in it with like a certain hashtag, then like some emergency telescopes will all point to the same part in the sky. So like if you're an astronomer and you're outside and you're like, oh my God, I'm watching a supernova, you can like tweet and all of these high grade telescopes will be like, supernova, and all of them will point there right away. So it seems similar in, just like commanding all of these, observatories to go look at the same spot. It's very cool.
Yeah. And this is going to sound probably counterintuitive, but it's a lot easier to do that with something that's really far away, like a star or a galaxy or a supernova, than it is to do with a planet. It's actually really hard to use big telescopes to look at planets.
Right.
Shockingly enough.
Well, because
that's a whole thing.
You're resolving actual stuff, versus looking in the direction of a point source,
Yeah. We really don't, we don't have a space telescope that is designed to do solar system studies.
Right.
Like we use Hubble, we have to fight for time on Hubble, which is a challenge in itself. But then even, like looking at pictures that we found of Mars with Hubble, they're really not that great. Like we get better images with the spacecraft that we send.
Right.
And even from here on Earth, sometimes we can get better views of Mars than we do with Hubble because it's just not designed for that.
Well, what do you say we jump into our interview with Dr. Singer and learn about some craters?
Let's do it. So today we are talking with Dr. Kelsi Singer, who is a planetary scientist with the Southwest Research Institute, or SWRI. She specializes in geology and geophysics of planetary bodies. And her most recent contributions have been as a co-investigator and deputy project scientist on the New Horizons mission, working in operations and on the geology and geophysics team. She recently received the Harold C. Urey Prize from the American Astronomical Society's Division for Planetary Scientists, which is the highest prize that DPS, or the highest honor that DPS can give for a young planetary scientist, recognizing outstanding achievements in planetary research. And today, specifically, we are talking about a subject that is very near and dear to my heart, craters. So, welcome. Thanks for joining us, Kelsi.
Thanks for having me, and thanks for the very awesome introduction.
We try. So I'm sure most of our listeners probably know what a crater is, but maybe not how important they are for understanding things like planets and moons and asteroids and everything. So from maybe a scientific kind of standpoint, what is a crater? How are they formed? And what are some of the things that we can learn about a body based on its craters? I know it's kind of a big question.
It is a big question, but that's fine. Well, we'll start at the beginning and with the basics. Crater forms when a piece of space debris, let's call it, hits the surface of a planet and basically forms a depression or a hole in the ground. And you can think of throwing a stone at a sandbox, for example. And when you do that, you would see a bunch of sand flying out, and you might see a dent left in the surface of the sand. And this is sort of similar to what happens in a larger planetary impact, but there's a lot more energy involved. And that's because usually the speed of the impact is a lot higher, and often the size of the impact is a lot higher, although there's a range of impacts that happen all the time, from tiny, sand-sized particles hitting the surface of a planet to much larger chunks. And right now, a lot of the impactors that could be happening, say on the moon, are from small either asteroids or comets. Typically on the moon, for example, the impact speed is about 15 kilometers per second, which is comes out to about 33,000 miles an hour. So it's a lot faster than you can throw a rock at a sandbox.
I did try that once. I was playing with a little AR thing and I tried to make a crater and it did not work. I was afraid to break something, honestly.
Yeah, well, that's fair. But these planetary impacts are speeding around, and they form craters occasionally, not so often anymore, lucky for us on Earth. Although there have been some famous impacts, like the very large impact that we believe probably caused the end of the poor dinosaurs. So impacts have been important throughout the history of Earth and also throughout the history of other planetary bodies. They're basically one of the many geologic processes that forms the surface that we see today. And people might be familiar with all the impact craters that are on the moon, but there's impact craters lots of other places in the solar system. There's impact craters on Mars, there's impact craters on Mercury, there's impact craters in the outer solar system where Tara and I both work on some of the moons of Jupiter and Saturn and even Neptune. And I even study impact craters all the way out as far as Pluto.
And beyond, right? With the
Yes.
Eric Koth body. I think
I know, it's like, how far out should I go?
as far as we possibly can. Yeah, I'm pretty sure there's craters on I don't think we've found anything that doesn't have craters on it. I mean, aside from like gas planets.
Yes. So of course the giant planets, Jupiter itself and Saturn itself, because we can't see any solid surfaces. We don't see impacts there. There is one other possible good exception, and that is Jupiter's moon Io. So Io is the most volcanic place in the solar system, and it's the reason we haven't seen any craters there is because it's constantly being resurfaced, and so it's got like a super, super young surface. That actually would be a good place to say one of the many reasons that craters are very useful in science, and that is because they're kind of like a time marker. And we say that because craters form over time at a somewhat predictable rate, not like once a second, but statistically they happen at a certain rate. And so if we see a surface that has a lot of craters, we can say we know that surface is an older surface because it's had time to form craters. Whereas if we see a really young surface, like Io that I just mentioned, we know that something has happened to erase those craters that formed. And so we know that that's a much, much, much younger surface that we're looking at.
And that is to say that the surface itself is young, not the moon, right? Io is old with the rest of the stuff in the solar system, so to speak, right?
Yeah, that is a great distinction. So it's a kind of an interesting thing to think about the age of planetary bodies, because as Colin was just mentioning, you have the interior of the body, you have the surface of the body, and those are interacting with each other. But the very surface is where the impacts form. And so if you have, say, material that comes up from the interior of the body and like in a volcanic situation and then flows out over the surface and makes basically a new surface, that means that the very surface is new, but not that the material was just created or that the body itself was just created.
Are there any examples of impacts like making the surface young, because of the impacts? Like if something is so bombarded, do you say in crater science that the surface is young again because it's been so impacted that it's been changed altogether by these impacts, or is that something where you would say no, that's simply an old surface that has lots of impacts?
That is also a very good question because, again, it kind of gets to like what part do you want to say is young or old, and which kind of science questions are you trying to answer, and that will kind of tell you which parts you care about if you can think of it that way. And an example might be some of the very, very large craters. So we have craters on the surfaces of some bodies that can take up, I don't know, something like up to, let's say, an eighth of the surface or a fifth of the whole surface of the body, which may or may not seem like a lot, but that's a pretty big area. For example, that would be something like the whole size of North America on the Earth, if you had a crater that big. And we see craters that big on other places. And so that whole area that the crater took up would be an area where the previous surface was not there anymore. And you are seeing down into the subsurface, which is another thing that craters are great for. They dig a hole for you, which we so far have not been very successful at doing it on other bodies ourselves. And so you can see down into different materials in the subsurface. And those different materials in the subsurface do tell you a lot of good information. Now, whether you decide that's a younger surface or not is up to what kind of study you want to do. So it could be that that surface was just sitting there and you just exposed it. So that's kind of a different type of new surface than if you extrude material from the inside and kind of form a new surface. So it's really not like maybe not a yes or no answer. It's more of a what do you want, how do you want to interpret it kind of answer.
I guess that kind of opens the door into a very broad question, which is when you and your fellow crater scientists set out to look at, say, a given crater, what are you looking for? What characteristics, help you make your predictions and conclusions about, what it is that you are studying?
Well, there's plenty of things to look at with craters, and we both look at and study the craters themselves to understand how the impact process occurred. And we also, as we've been talking about, use the craters to understand other things about the body, like the geologic history of the body. So one thing that's useful is if you look at a range of crater sizes. And if you start with small craters, they have a certain form and shape, and that's mostly kind of a bowl shape, we say. And that might be the kind of crater that you're more familiar with, or even Meteor Crater in Arizona kind of has this bowl shape and then a little rim sticking up. And as you get to larger and larger craters, those structures start to change. They become a kind of flatter, more pie pan shaped, if we're going with the food analogies. And they often form what we call a central peak in the middle. And as you keep getting to bigger and bigger craters, those structures change again. Instead of having a peak in the middle, you can have a peak ring. You can have multiple rings. And all these things tell us about both how the crater itself formed and what the surface that they formed in is like what kinds of materials are there, how strong are those materials.
You mentioned that the number of craters that you see on a surface can give you some information. Is that something that has to be hand counted, or do you employ like artificial intelligence and feed it an image of a surface and then the computer says, oh, here's how many I see, so that you don't have people sitting around counting?
There are lots of people working on trying to find ways to use automated methods or artificial intelligence to map craters. And it turns out it's a super hard problem because you don't usually have just a nice flat surface with a crater in it. And the artificial intelligence is really doing a lot of what our eyes and brain do. It's the same thing if you look at just a photograph of a mountain, you can still tell that it's a mountain, and part of that's because of the lighting, the way it's hitting one side but not the other side. And that's the same kind of things our brain does to try and find craters. But it turns out that most planetary surfaces are not a nice smooth surface with a crater in it. So doing the automated stuff is really hard, which means that we do a lot of work just looking and using other kinds of data that we have. Like sometimes we have topography data, which tells us the highs and lows to try and find the craters. So unfortunately, there's still a ton of manual work to be done, but that keeps us in business.
Shout out to all the crater counters out there. That was one nice thing about working on Europa, because there's really only like 45 craters that we can see right now, as opposed to the moon with like millions. So crater counting on some of these bodies is really simple.
Yes, and there's all in between. There's craters, bodies, as we were mentioning, with few craters, and there's bodies with many craters, and that's actually great to have that variety, because we get to see young areas like Europa, and we get to see old areas like the moon. So it's a nice mix. It helps us understand these different bodies.
I wonder if that would be a good spot. A while ago, we interviewed some citizen scientists who did a project where they built a tool that anyone could go and characterize, like the original Galaxy Zoo. Is that something that that seems like a great application for crater identification, feed an image and then just have anyone say this is what a crater is, this is not, what a crater isn't, and then just have people categorize it themselves. Is that a project that has happened that either of you are aware of?
Yeah, there have been people working on that, and I'm not sure the name of the project. I apologize. But that is exactly right. The craters are also a kind of a ubiquitous feature, and after just some time looking at them, you can be trained. Anyone can be trained to look at these and say, I think this is a crater, I think it's not. You might be wondering like how hard it is, and it just really depends on the geologic setting. As we were talking about, some areas have nicer, easier to count areas because the background terrain is pretty smooth. Other areas, you might have a bunch of craters on top of each other and it's hard to tell, or you might have had a lot of erosion like we have on Mars, because Mars has an atmosphere and a climate. So there's a range of how easy or hard it is, and certainly anyone can learn to identify craters.
I get that. Somebody asked me the other day, there was a news report that came out saying that people had just found a crater in Australia that was like kilometers across. And somebody was like, how did we not know this was there? And it definitely comes down to a lot of, like, especially here on Earth, we have erosive processes. We've got wind and water and volcanoes and all sorts of stuff that can kind of cover those up or wash them away. And we have no idea that they're, or, plants grow on top of it. It fills in with life. And so it's really, sometimes it can be really hard to actually identify some of these craters.
That's very true. And Earth is an interesting place to look for craters, partly because we can then actually go there and check out some more of the structures. And there's a lot of tectonics even often involved in crater formation. But as Tara was saying, we have all these other geologic processes that do a very good job of erasing impact craters. And there's a few nice examples, and then there's a lot of examples that are really hard to find. And so I don't think it's terribly surprising that we've found more craters recently, even since when I started in this field about 10-ish years ago. I feel like we found a lot more craters on Earth. We have better data. People are looking for them. People know what to look for more than we used to. It would be interesting to compare how many craters there are on Earth that have been found so far versus Europa, because I think there might be more.
There might be.
Yeah, or something close, equivalent.
I think that is a perfect segue into the next question we wanted to ask is, how do we get good information on craters that are really far away, say on Pluto or, really, really far out there?
For the most part, in order to study these other bodies, we have to send spacecraft there. Even for the moon, we can see a fair amount of the moon from Earth, and our high-powered telescopes can see pretty well on the moon, but it still really helps to have a spacecraft there. For example, right now, there's a spacecraft around the moon called the Lunar Reconnaissance Orbiter, which I worked on for a short time. And the spacecraft can look down directly on any spot on the moon. And it can look to the side, and it can take all different kinds of angles and images, and that really helps our understanding. Other missions are not orbiters because it just takes too much money and too much fuel to be able to do that. So, for example, Pluto, like you mentioned, was visited by the New Horizons spacecraft, and I also work on that spacecraft. And that was just a flyby. So it got to Pluto, flew by, went around the side, looked back, and kept going. And we were able to do a lot from that as well. So even our very high power telescopes, either on Earth or in space, like the Hubble Space Telescope, they cannot see craters on Pluto. Pluto's just too far away. So in order to study craters there and in other parts of the outer solar system and even on Mars, we really need to send spacecraft.
Something that I've always thought, I didn't always wrap my mind around is, we have this film at the planetarium called Incoming, which everyone listening should come see once the building is open again. It's a great film.
I want to see it.
Yeah, full dome. It's super fun. And one of the things they talk about is how we identify, and please correct me if I'm saying this incorrectly, but the Chicxulub crater in the Gulf of Mexico, which is that same crater that you kind of briefly mentioned earlier. I think, right, that we are crediting that impact with the extinction of the dinosaurs. And in the film, they talk about how it's like these concentric rings of magnetism. They talk about using magnetism or like, I actually don't know the details of it. Does that ring a bell? How can you detect a crater using something like magnetism?
Yeah, that's a great question. And that's not my area of expertise. But there are so many different ways that we can try to find craters, both on Earth and on other planets. We talked a little bit about just using images and in our eyes, but there's lots of other kinds of data. So they really big impacts really disturb the crust. And so you get these kinds of effects, like Colin was mentioning. You can get magnetic effects. You can get just kind of a redistribution of the mass of material, and that's a signature that can be seen by some spacecraft. And if you're able to actually go to a crater on Earth, like they are with the Chicxulub impact, even though it's underwater off the Gulf of Mexico, they're able to do drilling, and they can take rock samples back. And impacts are so energetic, and they cause what's called a shock to pass through the surface. And so that leaves a signature in the rocks. And so you can sometimes see these minerals that form from shock. And that's one way that people try to confirm, at least on Earth, if something is a crater or not.
I think with Chicxulub itself, it was one of those where the Earth's crust naturally has magnetic sort of layers because the poles switch and all of this fun stuff. But I think it just disturbed that so much that they can see how those layers have shifted. And it does kind of make the nice concentric rings that we normally look for in really, really big impacts like that.
Cool.
Got it. Man, that's nuts. And it's just so crazy to be thinking, because you mentioned it, Kelsi, it's underwater, right? I mean, this is like the Gulf of Mexico. So imagine, just like, that's just crazy that is something that we've been able to figure out. So there you go.
And a lot of that work has happened relatively recently. I mean, people have been working on the impact itself for a long time, but they come to more and more conclusions and gather much more information about it that really helps us understand it. And that's true for a lot of the science that we're doing right now. There's tons of open questions, tons of work yet to be done, and people are constantly coming up with good ideas.
Are there any like anti-craterists, people that are like super like conspiracy theory or like think that craters are something that they aren't or anything of that nature that you're aware of?
I am not aware of that. I think craters generally, for better or worse, don't draw people's attention that much. That's my guess. And obviously, I don't know if there actually are some out there, but I don't know of any off the top of my head. I think mostly it's just us crater people like arguing over whether something is a crater or not, that kind of thing.
So earlier, before we started recording, this is some meta podcast stuff, we have all these preparations that we do, right?
Yeah.
And so this is the question, Kelsi, that you mentioned is like, maybe we should loop Tara into this one as well, because, it's maybe not as night and day as I'll ask it. But the question I have is, have there been any major breakthroughs in crater science, right? Has there been any new technique or technology that has allowed us as scientists to really like do a lot more with crater science? And so this is, I guess, a question I'm posing both to you, Kelsi, but also Tara, if you want to chime in. And, of course, Tara's also a crater scientist. So there you go.
Yeah, there's been a ton of breakthroughs, I would say, because in some ways, we haven't been studying craters for that long, not as long as, say, gravity. And early crater scientists did look at both craters on the Earth. A meteor crater in Arizona was a great example, actually, where they weren't sure for a long time after they initially started studying it whether it was an impact crater or whether it was volcanic. And this actually gets a little bit back to your question, because you can get depressions in the ground other ways, from other geologic processes. And even some volcanic stuff is kind of explosive because of the dissolved gases in the magma. So there was a lot of discussion, and they eventually came to the conclusion that meteor crater was made from an impact through various lines of evidence and a lot of time studying it. And then they also could make that connection to craters on the moon. And so it's kind of been an evolving science, and there's been lots and lots and lots of breakthroughs, because it's, in some ways still somewhat new.
And I think, going back to your question earlier, I think AI is on the edge of being a huge crater breakthrough too, as far as crater counting and crater identifying and things like that. I think if they can, people are working really hard on it, and it's a difficult problem, but if they can crack that and have some sort of automated crater detection, that could make our jobs a lot easier in some ways.
That's a great example. And as I mentioned too, there's tons of things we still don't know. And we can do laboratory work to try to understand that. We can look at craters on Earth. We can look at craters on other bodies. Craters on other bodies are great because they give us a different set of conditions. So on Earth, we have the gravity we have, but on the moon, there's a lot less gravity. So all these pieces come together, and of course, people are also just doing kind of theoretical equations based on basic physics, understanding how these processes occur. There's tons and tons of work left to be done.
That's one that I'm definitely looking forward to, is recreating planetary scale impacts. That's something we just can't do in reality.
Like, if you wanted to actually simulate a planetary scale impact, fully, is that even fathomable? How would you do that?
That's a great question. I would say we have done some maybe preliminary stuff along that line. If I were to just go with the flow here and say, there's been a few times that we've thrown things at other planets or other bodies. Not very often. We have a few what we call impact experiments in the real world. They also use basically high power guns in labs to shoot things and simulate impacts. But as Tara was saying, those don't really get to the scale of a planetary impact in the lab. So I don't know what you think, Tara, but the only thing I could think of is if we took a very large thing and threw it at another body with high velocity, which would be very difficult to do.
Yeah, I remember reading back from, the 40s when they were doing basically explosions in the desert to try to recreate craters. They would bury huge bombs and then set them off and see what happened, which is maybe not the best way to do things. I don't know, but now we're pretty much just regulated to computer simulations, which is what I spend a ton of time doing.
Yeah, well, those are obviously very helpful and becoming also very advanced. So that might be another example of the breakthroughs, is that people are able to basically do what we call numerical simulations of all the conditions that would happen on a planetary surface, but in a mesh on your computer. And they're getting a lot more sophisticated as well, and have been able to replicate more of the things we see in real life.
So, kind of on that vein, have you come up with any major surprises in your study of craters? Has there been anything that you're just like, wow, that changes things?
Amazingly, yeah. I'll give you one recent example. We sent a spacecraft to Pluto. We'd never been to Pluto. We didn't know what the surface was going to look like. Even the Hubble Space Telescope just had kind of this, you could only just see these patchy blobs of darker and brighter stuff on Pluto. That's the best we had. So now we have all these really detailed images of the surface of Pluto, and we were able to see some craters. And in addition to Pluto, Pluto has a very large moon named Charon. Charon's about half the size of Pluto, so they're very big relative to each other. And Charon also had impact craters on it. And this may not sound that thrilling at first, but we were surprised because there weren't very many small craters. There are still some, just not as many as we expected. And our expectations were based on the moon. And on the moon, there's big craters and lots of small craters, many more small craters than there are big craters. And on Pluto and its large moon Charon, we were able to use this lack of small craters to say that there's something different about the impactors hitting Pluto compared to the impactors hitting the moon. And so the impactors are what creates the crater, of course. And in the Kuiper belt, which is where Pluto lives, that's all the bodies past Neptune. And there's not very many as big as Pluto. There's a few, but mostly there's medium-sized and smaller objects there. And we were able to use that to say that the asteroid belt, which is what hits the moon, is different than the Kuiper belt, which is what hits Pluto and Charon. And we didn't necessarily know that in advance. The reason we didn't know is because our telescopes can't see all the small Kuiper belt objects. And amazingly, we're actually able to use the craters on Pluto and Charon to understand those smaller objects that we couldn't see any other way. And so the big surprise was that the Kuiper belt looked different than the asteroid belt. And why we care about that is because that means something about how those objects formed. And we are kind of getting a picture of the earlier parts of the solar system by going to the Kuiper belt, whereas the asteroid belt has had more evolution and things happen to it. And so it really helps us understand how the building blocks of the planets formed, for example. So all those smaller objects that eventually grew into larger objects, we're able to understand those smaller objects better just by looking at craters on Pluto.
I also found it really interesting when we were looking at the craters on Arrokoth, the Kuiper belt object that the same New Horizons mission flew by, which is pretty small in itself. It's only, 30 kilometers across, which is not big, but it had craters too. And so we can use the craters on even the small bodies to learn more about other small bodies that are tiny, tiny bodies that are out there, and things that, how these small objects form too.
Yeah, that's another great example. So I think some people might have a visual of the moon and you see some very, very heavily cratered areas, but we didn't really find that in the outer solar system. And on places that are small, like Arrokoth, which is kind of a fun snow person shaped object. It has a head lobe and a body lobe, we sometimes call it. We also didn't find a ton of craters, and that tells us that there wasn't a lot of impacts, and that means that there wasn't a lot of objects out there to impact Arrokoth. And we didn't know what it was going to be like. We could have gone there and found another very heavily cratered surface.
So, obviously, as Tara said earlier, Kelsi, you are quite distinguished as a scientist in your field. You've done a lot of really good work. I'm curious, what led to your success? How is it that you've gotten where you've gotten? And also, what plans do you have for the future? What's ahead?
Well, I'm very honored that you would say that. And as I'm sure Tara can also speak to, it's a lot of hard work, training to be a scientist and then practicing as a scientist. And I've also had a lot of great opportunities. I've had great mentors and great advisors, and being able to be on spacecraft missions was a huge boon to my career, and a good scientific boost in terms of being able to work with a lot of great data. So I would say, you work hard and you train in the subjects like you guys are training in, and takes a while to get up the learning curve. But eventually you're able to do your own scientific projects, and science is never in a vacuum, as we've kind of been talking a little bit about already. You work with all different kinds of people, and you come up with these new ideas. For example, I'm even working with some volcanologists on a topic other than cratering at the moment. And there's a lot of things to be passionate about, I think, in science, just because there's so many open topics and there's so many questions we have, still to answer. And even planetary science really helps us here on Earth, I always like to say, because we only have one example if we just look at the things on Earth. But we can understand all these geologic processes even better if we look at all the other examples on the other lovely planets that we have in our solar system. So I don't know if I would necessarily have any specific things to pinpoint about how I got here. It's definitely been a journey, and it's been a tough but also very interesting.
And do you have any plans about, things that you're really looking forward to, projects that are coming up, or things that you've had in the back of your mind that one day you're going to be like, guys, I have this great idea, and everyone's going to say, Dr. Singer, of course, we have to do this.
Well, yeah, I don't have my super secret, project file in front of me at the moment, but I will mention one type of object that's becoming a very interesting set of objects in the solar system. And that is this type of object called a centaur. And even I wasn't super familiar with them until relatively recently, but they're called centaurs because when they were first discovered, they had some aspects that were like comets and some aspects that were like asteroids. And they weren't quite sure what to do with these features. And as you might be familiar with, centaurs in Greek mythology are half horse, half human. And so that was a fitting name. And some reasons why they're kind of up and coming objects is because they come in from the outer solar system. They are Kuiper Belt objects that get kicked in closer by Jupiter. And so this is a great way to study these really fascinating distant outer solar system objects without going there. And when they're a lot closer to us, just naturally, they come to us. And centaurs also have a range of sizes. There's some fairly large ones, not as big as Pluto, but so there's some fairly large ones, and then there's also a lot smaller ones. And the reason some people say they're kind of like comets is because they have activity. So they have stuff that's basically being kicked off or shot off their surfaces. And we have no idea how this happens. And so that's kind of a new class of objects that myself and some others have been putting in mission proposals for new spacecraft missions in the future.
And one thing I wanted to ask too is, I'm always curious, what got you into studying craters in particular? How did you become a crater person?
Yeah, I think it was also kind of a natural evolution. I of course knew about craters just from studying planetary science. And I'm going to be completely honest with you. I originally thought they were super boring. Just because I didn't know much about them. You learn more on Earth about volcanology and tectonism because those are major processes resurfacing Earth. But I didn't know how amazing craters were and what a formative geologic process they are. Not to mention, many of them are just simply gorgeous, beautiful. There's some great pictures of these craters on various worlds, especially the moon, because we have this orbiting spacecraft. They've been able to take some kind of really nice side views, almost as if you were like standing on the rim of some of these craters. And I didn't know how much they could tell us about planets. But once I started working on craters, I just found this huge depth of different things you could study. And they're pretty ubiquitous on a lot of places, but even where we don't see craters, that tells us a lot. So it kind of was an evolution of learning about how interesting they are and how much you can do with them.
So did you study craters in grad school? Was that your focus, or did that come after you got your PhD?
I studied a whole bunch of different features in grad school. I studied these landslides, which are called long run-out landslides because they're huge. For example, on one of the moons that I work on Iapetus, there's an 80-kilometer long landslide. So I studied those. I studied tectonic features. I studied some features that could be considered potentially icy volcanism. And then I started studying craters. And actually, I originally got into it from studying what are called secondary craters. And Tara mentioned these earlier. But when you have an initial impact, all that stuff that gets kicked out some of those fragments that get kicked out make their own craters. And those are called secondary craters. And I even had a student this summer who was searching for potential tertiary craters, which would be stuff that get kicked out of the secondary crater. So you can see craters are kind of a rabbit hole, and there's many, many different aspects you can study about them. Then I just started doing more and more with craters.
Very cool. So we are just coming up on our time, but we quickly, we do this fun thing where we invite listeners to send us in questions that they might have about, whatever given week's topic is, or just in general. And then we can forward these questions on to you, Kelsi, our professional crater scientist, to answer some of these. So our first question, coming from Hubert in Georgetown, is which has more of an effect on crater formation, velocity of the meteorite or density in the surface?
That is a great question. And the question gets at kind of the two main aspects of what we look at when we form craters. There's different characteristics of the impactor, and there's different characteristics of the surface that it's hitting. And the question was about the velocity of the impactor and the density of the surface. And in most cases, the velocities are so high that the surface density doesn't matter too much. But there is a time when the surface density does matter, and that's if you have either a smaller impact or a lower velocity impact, because you can kind of trade those off. For example, you can get the same size crater from a smaller, higher velocity impactor or a bigger, lower velocity impactor. So there's a lot of different things that can be traded off there. But when the density of the surface does matter, or the strength of the surface matters when you have smaller impacts. And in that case, that can really shape what the crater looks like.
And so our next one is from Brandon in Furlong, Pennsylvania, who wants to know, why do craters curl up at the edges? Why aren't they just like flat?
Yeah, the particular shapes that we see, either like the kind of bowl shape with the little rim, or even more of some craters do have flatter floors, but as you mentioned, they still have this edge that goes back up. And that's because at some point, there's just one point, let's say, where the impact actually hits the surface, and then the rest of the crater forms from a shock wave that propagates out and passes out through the surface, and that kicks out the rest of that material. But it doesn't have an infinite amount of energy. So at some point, the shock wave starts to slow down, and it just doesn't have enough energy to keep kicking material out. And so basically that feature you're asking about forms just from not having enough energy to keep continuing to excavate a crater.
Got it. All right, moving on. Mac from Weston, Massachusetts asks, how much of an asteroid is left over after an impact? In other words, how much gets vaporized and how much remains?
Yeah, this has been a topic of debate in our field for a long time. And again, in some ways, it depends on that impact speed that we talked about. And if you have mostly, which we do often have very high velocity impacts, the impactor itself either gets vaporized or fractured and broken up and spit out. So you don't very often see impactor left, say, in the middle of a crater. For a variety of reasons. Unless, as we talked about before, if you have very low impact, sometimes you might have it left in the middle. So it really depends on the speed and energy of the impact. But in most of the planetary cases we see, there's not very much left of the impactor itself. Tara actually works on this topic, so she should
I did. I have done a little bit of work on this, and I know even with impacts into something like ice, if we have an icy impactor hitting an icy surface, we see almost none of that impactor left over. So it's really interesting to see how that all works, I think.
Yeah, and as a lot of
that the
sorry, there was a little delay. Go ahead, Colin.
Sorry, I think my internet is pooping out there for a sec. I was just going to ask, in the case of an impactor, we obviously, it kind of it vaporizes and breaks up on impact. Is the material itself fundamentally changed, or is it just broken up and dispersed in the impact? In other words, like, is the impactor still there if you could pick up all the pieces and put it back together, or are those pieces no longer what the impactor was originally? Have they been changed to the point where you can no longer, even if you could, spend an infinite amount of time picking up the pieces, you couldn't do it because they're not the same anymore?
Well, I'll start, but Tara should chime in too. There's also something we haven't mentioned before, which is different types of impactors. And on Earth, for example, meteorites and the little chunks of things that we have left over that make it through the atmosphere, some of them are metallic, some of them are rocky, and then we also have icy impactors. And the metallic ones, a lot of times they might get melted, a little bit vaporized, but some of it is left. And Meteorite Crater in Arizona is a good example of that. They do have some really big chunks of the impactor left, and they still find little chunks all the time around the outside of the crater. But for an icy impactor, you might end up with some icy fragments, but you're also going to vaporize some of it. And the same thing with rocks. It sounds funny to like vaporize metal or rocks, but these are just such high energy that that's what happens.
In fact, the next time you come to Fisk, you can see a chunk of the meteorite that created Meteor Crater in Arizona. We've got a big, like 120-pound chunk of iron that sits in our lobby. But yeah, I think you covered it really well. Like when we're talking about the far outer solar system, most of our impacts are comets, which are very icy. And so if that hits the surface, most of it, because it's so high energy, we're not going to find a whole lot of little chunks of ice left over or even a lot of melted bits. It's mostly just going straight into vapor, which if there's no air on the body, it can just escape into space or you just never see it again. So
gone forever.
Yeah, which is kind of sad, but but there's also occasions too where it can, fall back down onto the surface, especially if it's something more rocky that's a bit more substantial, and we can learn a lot of stuff from that too. All right, so we'll move on to our last question here is from Mark from California. What's the farthest distance debris from an impact crater has traveled? Maybe not specifically, but sort of in a general sense.
Sure. This is actually something that I do work on, so it's a great question. I mentioned a little bit earlier about the fragments flying out when you were forming the impact. And some of those fragments land nearby and make those secondary craters, make craters themselves, and some of those fragments just keep going. So the impactor imparts energy into the surface, and that gets converted basically into velocity of those fragments. And some fragments reach what we call escape velocity for whatever body, let's say the moon. And that means that they can leave the moon. And some of them might come back to the moon, and some of them might just keep going. And partly that's how we get meteorite samples on the Earth from different bodies. For example, the Martian meteorites had to have been ejected in an impact. And so they were imparted with enough velocity to make it all the way to Earth. And so there's probably pieces of all different places of in our solar system at different places in the solar system. So they can travel quite a long distance.
Let me ask, because you said you've done some studies in volcanology too. Do volcanic eruptions ever have particles that reach escape velocity? Is that a thing that happens?
That's also a great question, and not something that I have ever heard of. I would say that's not even close to the types of energies that we're talking about for impacts. Even though volcanism can seem very active and very impactful on Earth, because we have to live with the consequences of volcanism. But nothing really gets ejected at those speeds. So you probably would not confuse a meteorite with a volcanic ejection.
Got it. I see also that John from Boulder has a question. John, producer John, jump in. What do you have?
Hi. So talking about escape velocities, what we're talking about right now is escape velocity from the originating body. Have we ever seen any evidence of an impactor having so much energy that it actually causes the particles to escape from the sun's gravitational well?
That is a great question. So basically, if the fragment could leave the solar system?
Exactly, yeah.
I think that would be pretty tough.
Yeah.
I have not heard of that happening, but that is a great end member example of kind of the range of energy that we're talking about. And so we can get between different bodies in the solar system, but probably not actually leave the solar system.
Gotcha. Okay. Thank you.
What a great question, John from Boulder.
Yeah.
Now it's got me thinking.
I love that one.
What would it take?
Yeah. Well, what about like in the far solar system, right? In the outer solar system, a high energy impact out there when stuff is already, about as far away as you can get before you're not really part of the solar system anymore. Like how would you have to be going significantly? Would you have to have some ridiculous amount of energy? Because obviously, if you're much closer to the sun, like in these inner rocky planets, then you have a long ways to go before you can say you're not in the solar system anymore, right?
Yeah.
You have this crazy energy. But what about if you're already right at the very edge? So
I feel like you're starting to form your new spacecraft mission already.
Yeah.
to study this.
I like it.
Well, I will say that if there's a twist of fate that makes that difficult to do, and that is because the impact velocities in the outer solar system are much lower. And that's just probably kind of what we've been talking about already. The dynamics are less, things are just quieter in some of those parts of the solar system. And so just by a twist of fate, we do not have really high impact velocities out there. They're still kind of fast. Like on Pluto, it's about 2 kilometers per second. But that's a lot lower than, say, 15, 20 kilometers per second, even up to 35 kilometers per second that we can get on, say, Mercury. So, yeah, unfortunately, it probably still doesn't happen. But that was a great way to try to make it happen.
Sounds like a grant proposal, at least.
It does.
And I will just jump in with one last thing that John also looked up for us. There are 190 confirmed craters on the Earth and only 41 on Europa. So
there you have it.
There you go. All right. And with that, we will finish for today. Thank you so much for joining us today, Kelsi. This was fascinating.
Yeah, thanks for your awesome questions. I've been very inspired and I'm thinking of a few new things myself.
Excellent. Okay, well, that is our episode for today. Thank you all so much for joining us, and a special thanks to Dr. Kelsi Singer for coming on and chatting with us today. It was super fun. Be sure to come back next week. We're going to be talking about astronomy education with Dr. Seth Hornstein. He teaches a lot at CU. He's taught me in a couple classes. He's a really fun guy, and he's going to tell us a little bit about how you teach astronomy and what difference it makes and how we're educating the next generation of future astronomers. Now we want to invite all of you to visit our website, www.colorado.edu/FISC. There you can see a schedule of all of our upcoming shows with topics and guests. There's also an option for you to submit questions for our experts to answer in our Capcom Q&A segment. So if you have any burning questions that you'd like to hear answered on the air, definitely send us a message. You can also use our website, our email to send us your questions, fiscpodcast@colorado.edu. Also on the website is an option to donate if you would like to help us continue in our podcasting endeavors. Obviously, funding from the university is a bit sketchy right now, so we would love to keep bringing you some really fun astronomy content. And so if you'd like to help us out with that, this program is made possible by viewers like you. So thank you very much for considering. Also, don't forget to comment and subscribe and like our episodes to make sure that you don't miss any of the upcoming ones. Our podcast is available on YouTube, SoundCloud, Spotify, and Apple Podcasts. Otherwise, thanks again. We hope to see you next week.